Today we're going to be reviewing the gas laws, which compare the different aspects that affect gas pressure and their mathematical equations that you will use pretty much all the time in chemistry. So first we're going to talk about Boyle's law. Boyle was a scientist who studied volume and pressure, their relationship. So he basically studied different samples that were under a constant temperature, and then he manipulated their volume and saw what the change in pressure was. When he did this, he found that they had an inverse relationship. So as one increases, the other decreases. Mathematically, the way that he expresses this inverse relationship is P times V equals K, this constant. So if you increase the volume, pressure would have to lower mathematically so that this number, K, is always constant, always the same. Same goes if you were to increase pressure, volume would have to decrease so that this K stayed constant. And if we were to graph this relationship, it would look something like this. So a lot of times on AP test, multiple choice question would be like, which graph best depicts Boyle's law? And you would want to pick one that looked like this. It shows an inverse relationship. We can also compare changing conditions for a given gas sample by saying P1V1, so initial pressure, initial volume, is equal to P2V2, the ending pressure and ending volume. If we have one unknown for the ending pressure or volume, we can mathematically solve for what that should be based on Boyle's law. So here we have an example. Oxygen gas with a volume of 425 milliliters. When the pressure is equal to 387 kilopascals. We allow the gas to expand to 1.75 liters, and we want to know what the new pressure is. One thing to keep in mind here is units. For pressure and volume, what the unit is for the given question or answer, unless it tells you what unit it wants, doesn't really matter. Okay, what matters is that we are consistent in our math so that units cancel and we get the right unit, right value in the end. Okay, so the first thing I notice, we have kilopascals. Usually we use atmospheres, but kilopascals is totally fine. There's no other pressure given. We just have to know that our answer, pressure, is going to be in kilopascals. Then I'm looking at my volume. I have milliliters and liters. These will not cancel out mathematically if I keep them as is. So I either have to convert 1.75 liters to milliliters or change 425 milliliters to liters. Does not matter which one I do. I'm going to end up changing this one to liters because I like liters better. But you could easily change 1.75 to milliliters as long as they are the same. It doesn't matter. We'll talk about temperature later. But for now, for volume and pressure, doesn't matter what it is as long as you are consistent. So here I'm going to lay out my equation. P1V1 equals P2V2. Our initial pressure is 387 kPa. Our initial volume, I again convert it to liters, so that's 0.425 liters. And our final volume is 1.75 liters. So now I want to solve for what the final volume is, or sorry, the final pressure is, P2. So I can use this equation and essentially rearrange it to set it equal to P2. So to do this, I have to divide both sides by V2. So what we get in the end is P1 V1 over V2 equals P2. Once I rearrange my equation, it's a simple matter of what I say, plug and chug. You plug in the numbers, plug them into your calculator, and chug out the answer. So I'm taking P1, which is 387 kilopascals, multiplying by 0.425 liters, and dividing by 1.75 liters. In the end, I get in my calculator an answer of 93.99. And again, my unit is going to be kPa because that's what I'm left with, kilopascals. Okay, so I have solved for P2. That's all to it. Next, we're going to talk about Charles' law. Charles compared temperature and volume under a constant pressure. So he kept pressure constant and then manipulated temperature to see what it did to the volume. He found that they have a direct relationship. So if you increase one, the other one's going to increase. If you decrease one, the other one's also going to decrease. Mathematically, the relationship looks like V over T equals K. K is again a constant. So if you think if this constant isn't changing, if it's always 1, if you increase volume, you have to increase temperature as well to keep that value the same, to keep it 1. And again, this can be used to compare a sample under changing conditions as long as pressure is constant. So we take initial volume over initial temperature equals final volume over final temperature. For temperature, the unit has to be in Kelvin. Mathematically, it will not work out if you use Celsius. If you want to try it, you will see it will not work out. So we have to use absolute temperature for these gases. So temperature must always be in Kelvin. So here we have a balloon with a volume of 2.2 liters and a temperature of 22 degrees Celsius. Balloon is heated to 71 degrees Celsius. We want to find a new volume for the balloon. Okay, first thing I notice is that we're not given temperature in Kelvin, so you will want to convert these Celsius temperatures to Kelvin. The volume is in liters, perfectly fine. That's just going to tell us that our answer is also going to be in liters. So we're going to set out our knowns and unknowns. Initial volume, 2.2. Initial temperature, 22, of which if we add 273, we get 295 Kelvin. Final temperature, 71 plus 273, is 344 Kelvin. And we are solving for the second volume, our final volume. Once again, we can rearrange this equation to set it equal to V2. To do that, we have to multiply both sides by T2. So I'm going to have V1 times T2 divided by T1, or T initial, apparently I just felt like putting T initial there, equals V2. And once again, we can plug and chug. You could also do like cross multiplication kind of thing. However you want to do math is fine as long as it's valid. I like to rearrange equations. So here I'm taking 2.2 liters, multiplying by my final temperature, T2, 344, always got to keep it in Kelvin, don't want it in Celsius, dividing by our initial temperature, which is 295 Kelvin, and I get an answer of 2.56 liters, because initially I'm given liters. Okay, you can also, for these problems, just always take a second and analyze your answer. Does it make sense? So here we increase temperature from 295 to 344. Since temperature and volume have a direct relationship, my volume should also increase. Did that happen? Looking, 2.2 is smaller than 2.56, so yes, my volume did increase. That answer makes sense, and I feel more confident moving forward that that would be the correct answer. So always, it's beneficial to take a second and just analyze your answer with these, just to make sure it actually makes sense. And finally, we're going to talk about Gay-Lussac's law. This identifies the relationship between temperature and pressure at a constant volume. How do you know the volume is constant? Usually the question will say something like a rigid container. So that means like a hydro flask. Your volume's not going to change, whereas a balloon, your volume could change because it's a flexible container. Just like temperature and volume, temperature and pressure have a direct relationship. So as one increases, the other also increases. So Gay-Lussac's law looks a lot like Charles's law. It's just he's using pressure instead of volume. So again, we have P1 over T1 equals P2 over T2 when we want to compare a sample under different conditions. And just as before, our temperature unit must be Kelvin, not Celsius for these. So here we have a gas in an aerosol can. That means it's a rigid container under pressure of 3 atmospheres and a temperature of 25 degrees Celsius. It's dangerous to expose aerosol cans to high temperatures. Usually there's a warning on like hairspray cans and things like that. But what would the pressure in the can be if we put the temperature, put it in some sort of oven or something at 845 Celsius? So here we're comparing pressure and temperature. So I'm using Gay-Lussac's mathematical equation. Our initial pressure is P1 equals 3 atmospheres. Initial temperature is 298 Kelvin. Final temperature is 1118 Kelvin. We want to solve what is that final pressure going to be. So once more, we can rearrange this equation to isolate P2. We do that by multiplying both sides by T2. So we're going to have P1 times T2 divided by T1 equals P2. And from there, I am good to plug and chug. So I put in P1, that's 3 atmospheres, times T2, 1118, and divide it by T1, which is 298 Kelvin. And I get P2 is equal to 11.26. What is my unit going to be? Well, if I look, P1 was in atmospheres. Then we had Kelvin for T2 divided by Kelvin for T1. Our kelvins cancel out and we're left with atmospheres. So that is 11.26 atmospheres is our final pressure. So that's very high pressure compared to what we started with, which is why if you were to put an aerosol can in a flame, not smart, it would explode. Okay? Next, we're going to be talking about the combined gas law. So this combines Gay-Lussac's, Charles, and Boyle's law all together. We're comparing pressure, temperature, and volume for a fixed amount of gas. Amount means like number of moles, number of molecules, number of atoms of gas. So the only constant that we have is the number of moles or molecules or atoms of that gas. Everything else could change, and we could compare those answers to solve in a given problem using this combined gas law. P1 V1 over T1 equals P2 V2 over T2. So really we just literally combined all three of those into one equation. Once more, temperature has to be Kelvin. Pressure and volume, as long as you're consistent, it could be hypothetically anything. So here we have 2 liters of gas at 35 Celsius and 0.833 atmospheres, and we bring it to standard temperature and pressure. And we want to know what will the new gas volume be. So here's our combined gas law. Our initial volume is 2 liters, initial temperature is 308 Kelvin, remember to add 273, and our initial pressure is 0.833 atmospheres. Our final temperature, standard temperature and pressure means 0 degrees Celsius. 0 degrees Celsius is 273 Kelvin. Standard temperature and pressure also means 1 atmosphere, so our second pressure is going to be 1 atmosphere. And we're solving, I guess I didn't put it there, the new volume, V2. Don't want that. So we're solving for V2 here. So to isolate V2, we have to multiply both sides by T2. So that would be P1, V1 times T2 divided by T1 equals P2 V2, and then we're going to divide by V2 to totally isolate, divide by P2. We're solving for volume, not pressure, my bad, equals V2. Okay, so now I'm going to double check my units, make sure that things are going to cancel. I have temperature in Kelvin, which is what I want. The atmosphere, or the pressure, are both in atmospheres, so that's going to cancel out. That's going to be fine and dandy. And my final volume is going to be in liters, because my initial volume is in liters. So now I am good to plug and chug for the final answer. So P1 is 0.833 times V1, which is 2, times T2, which is 273. Divide that answer by T1, which is 308, times P2, which is 1. And I get an answer of 1.48 liters. So that is my V2. Okay. In the next video, I will go ahead and talk about Avogadro's law and also discuss the ideal gas law. So let me know if you have any questions.